Okay. So that was, what was the number? Number 5. Okay. So if strontium is a red light, and it has a particular frequency for that red light, then if you draw a, like this, and your frequency is increasing that direction, and it's getting higher, then you have a visible range in this in here, but within that visible you have red on this end and blue on this end, because blue is a higher frequency than red. Then what they're saying is, what's the frequency of the light that precedes the red for strontium? And it would be this region, which is infrared. Yeah, that's what that means. Yeah, these pictures are good.
The color thing from like blue to red, is it not what it is? Are they?
I don't think so. No,
This,
they're not part of useful information. Yeah, you just got to know it. We might as well take the ones that are giving you trouble and just do them, because they're going to be recorded so everybody else can look at them. You didn't mark them? Okay, that's fine.
the ones that are all the work, like the ones that are good, like these ones are good because I just not good.
Oh, okay. Yeah. The ones that give you trouble are the ones that have weird wording.
Do you want to speak again?
Sure, that's no problem. 92. Okay. Let's see, here we go.
Great. State, I think, is that
Ground state. Okay, right. We didn't discuss that, did we? Ground state. Ground state in reference to an atom is you have your nucleus, and then you have your energy levels here, like that. The ground state is the closest that an electron can get to the nucleus without bumping into its neighbors. Which means, if it's hydrogen, then the ground state is right there in that first level. If it's helium, then you'll have another one in there. But if it's something like oxygen that has 8 electrons, so it'll have 1, 2, and then this level will have 6, right? 2. Let's see, we could have a maximum, this one is S and this one's SP. So we could have maximum 8 here, so we could have 6 electrons here. So the ground state would be at this level, All right, for oxygen, we would have 1s2, 2s2, 2p4. That's right. So the ground state would be right here. So when it says, so let's go back to the question. The energy of light emitted when a hydrogen electron goes from 2 to 1 is what fraction of its ground state ionization energy? Okay, ionization energy. So let's look at our hydrogen. Ground state ionization energy. That's the amount of energy it takes to go from whatever the ground state happens to be to infinity. How much energy does it take to go from ground state to infinity? So that is a certain amount of energy, the ionization energy, and from n to 1. Okay, so what fraction of the energy going from here to here is that? This is going to be less than that, but we want to know what's the ratio of the two. Okay. So let me see, how did I approach that problem? Since we're not given any value at all. So that means okay. We need to use the definition of calculating energy based upon the n value, that formula. Let's see. Better start over here. So the formula that we're going to use is this one. Okay. That's the amount of energy at any one level. So the difference in energy between, we need to calculate this energy here and this energy here going from 2 to 1, right, and compare them. Right? So in order to calculate 2 to 1, we need the energy of 2 minus the energy of 1. 1 for this one. Right? So that would be this one would be 1 because it's hydrogen. The Z number is hydrogen. So we would have 2 would be minus 2.178 times 10 to the minus 15. Is 1 squared over 2 squared minus 1, which would be this one. Actually, a minus minus a minus. Okay, 2.178 times 10 to the minus 18 times 1 again, this time over 1 squared. So that would be the energy for this one. And then the energy for this one would be going from, the ionization energy would be going from actually it would be going from here to there. So this one would be going from E1 to E infinity. So we would have E1, which would be this one. 1 over 1. And then subtract the minus 2.17. Times, what's this expression? Well, 1 is still z, but this one's infinity. So any number divided by infinity is 0. So that means that one goes out. So it would just be this value, and the ratio then would be, let's see, how was it worded? What fraction? So this one's going to be less than that one. That means this one's on top. So we want the ratio of this one divided by that one. And actually, we're looking for the absolute value. We only want the ratio of the two numbers. So we would take this value on top divided by this value on the bottom and resolve that. And what did it come out to? 3/4? Right. Probably put that one on top of this one. You might have to actually, yeah, you resolve the fractions. Hey!
Sorry, I'm like,
We were beginning to wonder.
well, it looks like.
It's kind of slim pickings today, yeah. I would expect Hunter to be here.
He's usually here.
Mm-hmm. Well, we'll do what we got to do.
What?
We were discussing number 92, and it's being recorded, so I'll look at it later.
See you.
Now that formula should be in useful information. Okay. I wouldn't expect you to memorize that one. Okay. We're going to try to cut it off at about maybe 2:45, 2:30 or 2:45. That should be enough time to review, and then we can move into the lab because I didn't do any explanation of the lab last week, did I? I don't think so, no. So let me talk about that for a few minutes. Okay. Oh, do you have a report for me?
Is it okay if I email it to you?
Sure. Yeah.
Thank you.
Does Blackboard Dropbox doesn't work very well?
Oh, no, that's fine too.
Okay.
Dropbox, that's what you prefer?
Either one, yeah. The nice thing about Blackboard is it automatically tells me if I've got any in the grade book.
Yeah.
And I don't have to go searching through my emails to find it.
Oh, yeah, I will definitely do that. That makes way more sense.
Got another one? Any questions from the audience? Let's see. Feel comfortable with the concept of that rainforest.
You did 19, right? So is that what I just did, you said?
That was 92.
Oh, you just did 92?
Mm-hmm, 92. We looked at, was it number 5 was the first one. Just to the one which required a picture. Understanding if frequency increases to the right, then we have the visible range in here with blue on this end and red on this end. So if strontium emits here, then what's just before strontium? Infrared. That's what number 5 is all about.
Okay.
Those are the only 2 we've done so far.
Did we do 19?
19.
Mm-hmm.
Okay. All right. Here we go. When an electron in a 2p orbital of a particular atom makes a transition to the 2s orbital, a photon of wavelength 629.1 nanometers is emitted. The energy difference between these two is. So we're going to convert, and that needs 19. The operative formula here is energy equals to H2. So Planck's constant times the frequency is the energy.
H is the constant, stands for constant.
Yes, H is Planck's constant. And that's given in useful information. Okay. So let me back over here. But we don't know the frequency. We know the wavelength, right? So remember the conversion, C equals frequency times lambda. So frequency is equal to C divided by lambda. Okay? So we just substitute that in here, and that gives us energy equals to Planck's constant times speed of light divided by lambda. Okay? Planck's constant, I probably got it right here. Here we go. So then energy equals to Planck's constant, which is 6.626 times 10 to the minus 34 joules seconds. And then this term has speed of light, 2.9979 times 10 to the 8 meters per second. Then we have to decide what goes in the wavelength. So if you look at your unit of measure, wavelength is a length, right? So we look for the length measure in here. And the length measure is meters, right? But it's given to you in nanometers. And so that has to be converted to meters. Here's the way I do it. 629.1, right? Nanometers. 629.1 nanometers. And a nanometer is 10 to the minus 9 meters. So it's times 10 to the minus 9 meters. Okay? Then you don't have to, I put it in here in scientific notation, but if you're in a hurry, that's the best way to do it without making a mistake. So it's nanometers and the conversion of nanometers to meters. And now all you have to do is resolve that. And seconds will cancel here, meters cancel there, and leave you with joules, which is your energy unit. And that should come out to 3.16 times 10 to the minus 19 joules. That's the energy of that transition. At that
C
wavelength.
is another constant.
C, yes, speed of light. It's not in there?
I'm sure it is. Oh, it isn't. Oh,
It's
wait,
not?
here it is. It's there on the left at the bottom. 2.99.
Yeah, there it is.
The C stands for the speed of light.
Mm-hmm.
I need to look that.
Right.
So really, that was just a bunch of stuff we had. And then you started to correct that.
You have another one? 85. Okay. Let's erase this one. Five. Eighty-five. Let me see what the problem says. Which of the following equations correctly represents the process involved in the electron affinity of X? Oh, this is definitional. So, electron affinity measures the amount of energy that is evolved when a neutral element accepts an electron. Right? So our element has to be neutral, no charge, plus it has to be a gas. Why would it have to be a gas? Because we want separate elements. We don't want any interactions between the element and any of its neighbors, right? Because that will bias the results. Okay, so that gas. And then we have an electron, and then that gives us a minus charge gas. Okay? That's just definition. While we're on the topic, how about ionization? Ionization energy. We have to start with the same situation, right? X as a gas. But in this case, we're going to remove an electron. Right? So when we remove an electron, we have a charge, still a gas, plus that free electron. The amount of energy required to produce that. So this, we have to put energy in. This, we get energy back. Okay, that's the comparison of the two. Start from the same place, right? But two different processes happen. In this one, you add an electron. In this one, you remove an electron.
Why does it have to be a gas again?
Oh, it has to be a gas because if it's a liquid or a solid, you have significant interactions between this one and its neighbor. And any energy transactions between this one and its neighbor will swamp the effect that we're looking for. Okay, so we separate them and make sure that they're gases first, then they're essentially independent.
Okay. Same thing with ionization, it needs to be a gas.
Yes,
Okay.
exactly.
Can we do 87 as well?
Oh, okay. Let's see, 87. Consider an atom traveling at 1% of the speed of light. The de Broglie wavelength is found to be 1.46 times 10 to the minus third picometers. Which element is this? All right. 7. De Broglie was a physicist. That's why they named it after him. Okay, so what information do we have? Let's put that up there first.
We have speed of light.
Yep, 1%
1%, yeah.
speed of light.
We have the wavelength.
Okay, and it's an atom. Speed of light, 1 atom is traveling at that speed. Its de Broglie wavelength is equal to 1.46 times 10 to the minus 3 picometer. Okay, so what's a picometer? Well, nanometer is 10 to the minus 9 meters. A picometer is 10 to minus 12. Yep. So that would mean this is if we multiply that times 10 to the minus 12, we get 1.46 times 10 to the minus 15 meters. See what I did? I incorporated this picometer measurement here into that value, and then it becomes 10 to the minus 15 meters. Okay. So that's what we're given. Now, how are we going to tell what the element is? What we're looking for, the concept here is that anything that's moving has a wavelength. If I were moving, I would have a wavelength, and it could be calculated. So this atom has a wavelength as it's moving. You know how fast it's moving. But in order to make the conversion, we need to be able to tell how much mass that atom has. Right? The mass and the speed will give us the information we need. So we know how to calculate the energy. Right? We can calculate the energy here. Remember the formula we put up there before was E equals Planck's constant times C divided by wavelength. Okay. So we can calculate the energy that this thing has. Actually, this is for light. But if we substitute in here, rather than the speed of light, we substitute the velocity of the particle. Then if you know the velocity of the particle, you can calculate its energy along with its wavelength. Right? So we just substitute V in here for C. Let's see. Right. The C would be at the speed of light, but we're only 1% of the speed of light. Also, but that's got no mass in it. Right? What formula has mass in it? Right? That's if the mass is moving at the speed of light. But it's not moving at the speed of light. It's moving at 1% of the speed of light. So velocity. Okay?
Those are just interchangeable?
Yes.
Okay.
Yep. The only time that you would say mc squared is if you had mass that was converted completely into energy. Then this would be C. But this is not converted into energy, it's only moving. Okay, that's the difference. Okay, so we have those two formulas, and we need to conflate them so that we can solve for mass. Right? So if we solve this one for mass, then that's E divided by V squared. And then if we substitute this sum of E in that E, then we have mass equals Planck's constant times velocity over lambda divided by V squared. Okay, so I just substitute this one right in here for that E. And then we can resolve that because we've got a V here and a V there. So this V is in the numerator, this V is in the denominator, which means, and this one's in the denominator, so it's also in the denominator here. So one of these V's cancels, that V cancels one of these V's, so we only have a V in the bottom, we've got a lambda in the bottom, and we got Planck's constant on top. Okay, so now we can find out what the mass of that atom is. We just need Planck's constant, 1% speed of light, and the de Broglie wavelength. So if we substitute those values in there, let's see, give ourselves a little bit more room. So Planck's constant is 6.626 times 10 to the minus 34 joule seconds. Okay. And then on the bottom, what's the velocity? Well, the speed of light, is 2.9979 times 10 to the minus 8 meters per second. But 1% of that would be 100th of that, right? Oh, excuse me, 10 to the 8. Whoa. That'd be a slow photon, wouldn't it? So that's 10 to the 8 meters per second. So 1% of that would be 100th of that, right? So it'd be 10 to the 6th, wouldn't it? Right? If 10 to the 8 is the speed of light, then 1% or 0.01 times that, 10 to the minus 2 times that, would be 10 to the 6th. We'll just change that to 6th. That's our velocity. Okay? And then our wavelength is the meters. So it's good that we changed the meters already. 1.46 times 10 to the minus 15 meters. Let's see. Check those units. Okay. Yeah, the units work out. I just wanted to be sure. So if we take that and check my calculations here. So 6.626 exponent there. That's not right. 6 exponent 34.7. Okay, then divided by the speed, and then divided by the wavelength. So I get, these are all SI units, so the mass is going to be in kilograms. Right? 1 times 10 to the minus 25 kilograms. That's per atom.
So an E equals MC squared, that's kilograms, the mass is.
Yes.
Okay.
Yes.
So we can use
The mass is always in kilograms. Mm-hmm. That's right. And now that we know how much, so this is kilograms per atom. But our molar mass, which is where we're heading, is going to be in grams. So 1.51 times 10 to the minus, that's 3 times, so it's 22 grams per atom. Right? Okay, so this is grams per atom. We're just doing some dimensional analysis now. We want grams per mole. We know how much it is for one atom, how much it is for a mole of atoms. Minus 22 grams per atom. Then we need to get rid of the atom, right? Denominator, numerator, and leave us with moles, right? So how many atoms in a mole? Avogadro's number, right? So if we multiply this times that, atoms cancel, and that's grams per mole. So 1.51 exponent times Avogadro's number. And that's 90.9. 90.9 grams per mole. Okay, so we just go over to the periodic table, find what's closest to 90.9. 83. All right, so the toss up.
So,
Could be that one or that one. 90.9 is almost 91. Probably zirconium. Most probably zirconium.
question. So when we're converting from kilograms to grams.
Oh, did I lose you there?
No, I just had a question about, so I know like typically we would just add the subscripts, superscripts.
Uh-huh.
Is it super at the top?
Yeah.
Superscripts.
Uh-huh.
But since they're two negatives, wouldn't it be to the 28th instead of the 22nd? I tried it in my calculator and that's what it's giving me.
Yes. Yes, you're right. I think you're right. Well, let me see. Hold on a second. Let's do unit conversion. How about that? That's the surest way to do it. Like that. Kilograms on the bottom, kilograms on the top here, right?
Yes.
Okay. So one of these is 10 to the third of those. So it is minus 22.
Yes. Okay. I was doing -3 at the top, but it shouldn't be that.
No, because that puts kilograms on the top. Both of them.
Yeah. Okay.
Yeah.
Thank you. That's where I got mixed up.
I should have stuck that in there just to be safe.
No, I get it. Sorry, long problem. Okay.
Say again? Oh, okay, sure. Which one? 119. Okay. The last one. The last picture show. Okay. So this one's going to be all right. The wavelength of light associated with n equals 2 to n equals 1 transition in hydrogen is so many meters. Okay. Yeah, that was using the same formula as before. Okay, what do we know? The transition is from n equals 2 to n equals 1. And we want to compare the transition for hydrogen versus lithium 2 plus. Right? That's important because this is hydrogen-like. Lithium has 3 electrons. If it's a 2 plus ion, it only has 1 electron left. So we're comparing apples and apples. 1 electron. But the Z value, the atomic number, will be different. Let's see. All right. So we're going to be using this formula. Minus 2, 10 minus 18. Z squared over n squared. And the transition, maybe I can put that in 1. And we have a delta E that we could incorporate here. So minus 2.178 times 10 to the minus 18. So we have from first minus second. Yeah, from this one minus that one. So we have this one would be C squared over, this is 2. No, that won't change. 2 here, and Z squared over 1.
Where did you get the formula from? I'm a little confused.
Let's see. It should be in there.
Oh, no, I see it. I always see after I
There it is. It's kind of 2/3 of the way down in the middle.
I see it now. What does Z stand for?
Top number of protons. So it's final state minus initial state. So, if it's final state, then this should be 1. And that should be 2. Final state minus initial state. Okay.
Wait, what does N equal?
N,
I know it's giving it sense, but what does it mean?
N is the principal quantum number or the energy level.
Okay.
So the transition from energy level 2, that's the nucleus, it's going from 2 to 1,
Oh, yeah, okay.
the electron transition. Let's see. And let's see. Look at the wording again. The electron hydrogen spectrum is 1.216. I don't even know if we need that. Oh, yes. Okay. Yeah, we do need that wavelength. Because the question is, what value do we need to multiply 1.216 times 10 to the minus 7th to get the wavelength for that same transition in the lithium ion? Okay. So we need to calculate the energy transition from one to the other and convert that to wavelength. Right. So we're also going to require the conversion of, let's see, energy of a photon equals h nu, and that's also h c over lambda. So since we've got wavelength, we need to solve for lambda. So lambda, we bring lambda over here, and E over here, we've got H divided by C over E. Okay? Right. So we're given the wavelength for the hydrogen transition. But we need to find out what the wavelength is for the lithium ion transition. I don't know why I put that calculation in there. You don't need it because we're given the transition for the hydrogen. So the hydrogen wavelength transition is already given as 1.216 times 10 to the minus 7 meters. Did I convert that? No, it's given that way. So that's hydrogen. What we need to find out is what's the same transition for lithium. Okay. So we're going to have this energy value incorporated in here. Then we can find out what the lambda is. So what we need to do is solve this equation for lithium. Okay. So the change in energy here is minus 2.178 times 10 to the minus 18. And then we want, in this case, Z for lithium is 3. Right? Because lithium has 3 protons. Whereas hydrogen, it was only 1. Right? We didn't have to do the hydrogen because it was already given to us. So we're going to do the lithium, and Z then is, N is 1, right, squared. And then N2 is 2 squared. And this one is 3 squared over 3 squared. Or 3 squared, 3 squared. I think. Those are the Z's for lithium. 3, it has to be squared. And then the energy level transition is actually from 2 to 1.
And we're getting up from the ends they gave us, right?
Yes. So this is going to be 9 minus 9 divided by 4. Okay, so let's see what that is.
Okay.
9. Yes? So that's 2.25 here, subtracted from 9. 6.75. 6.75. And that's times this value. 2.178. Yeah, 2.178. And exponent. That's a negative. So times. So this is minus 1.47 times 10 to the minus 17 energy. I think we can leave the negative sign out because we really only need to change in energy. Yeah. So now we can substitute in here the, let's come over here. Wavelength is the Planck's constant. I think. 626. I rounded it off. Okay. That's this term. And then 2.9979 times 10 to the 8. And then the energy is this term. 1.47 times 10 to the minus 17. Yeah. Okay, now let's see if I got that right. 2.9798. And I'm going to multiply that. No, I'm going to divide that by this number. And then multiply by that one. Okay, so I get 1.35 times 10 to the minus 8 meters. So this one is 1.35 times 10 to the minus 8 meters. So now all we have to do is ratio the two. Right? So the ratio of these two, we just call it K, is let's see, the wording, that's important, the wording. By what coefficient should this wavelength, 1.26, be multiplied to obtain the wavelength of the other one? So what coefficient do we have to multiply that one by? 1.216 times 10 to the minus 7 times some value to equal this one. Right? That's the way the wording is. So we divide this one by that one. Okay. And then 1.226. Divide that into that value. We get 0.111. Now, that's probably not one of the answers. No. So what you would have to do is resolve each one of these as a fraction, right, and see which one fits. So I think, well, let's just do, what's the first one? 1/9? 1 and 9, right, that's it. There you go. Seems like an awful lot of work for that one little answer. Question?
I got a little bit lost.
Okay.
After we got the 1.35 times 10 to the negative 8.
Okay. So we got that one from this calculation.
Right. Yeah, I got that.
Okay.
And
So
then
then-
what switched to?
Oh, okay. So now I went back to the wording of the problem. And the problem says, by what coefficient should this wavelength the wavelength that we're given, 1.216 times 10 to the minus 7, what number should that be multiplied by? So I said that one has to be multiplied by a number to give us this answer. And I did that so to be sure that my ratio in this worked problem was set up correctly. Otherwise, if I did it wrong, it would come out as 9 to 1 instead of 1 to 9. And 9 to 1 times that would not give you this. 1/9 would give you that. Okay. I'm exhausted. Okay. We're on time. We're doing good. Another one? Okay. Any trouble with electronic structure? Writing the S's and P's and D's.
You go practice.
Okay. Let's see if we can find one that fits the bill here. Okay. 25, starting with 25. That takes the basics. I mean, that's not writing the structure, but it makes sure that we know what the each one means. So how many F orbitals have the value n equals 3? N equals 3. So if n equals 3, what can L be? L can be either 0, 1, or 2, right? Okay? So, by convention, this one is S, this one's P, this one's D. So how many f orbitals can we have? 0. .5 is 0. You don't have any f orbitals in the n equals 3. Okay?
Do we use this for this?
Sorry. No, that's when you start filling the orbitals with electrons. You just have to know this.
Okay. Let me just.
Remember, principal quantum number, angular momentum, that's the next one? Yeah, angular momentum, magnetic, and spin. Those are the quantum numbers. So for each one of these, this one can be starting with 0 up to however many you have. So 0, 1, 2, 3 of them. And then this one will be, whatever this one happens to be, minus that number, whole number stepwise, up to plus that number. So if it were 2, it would be -2, -1, 0, 1, 2 for this one. That's m sub L. And then spin, of course, is +1/2 or -1/2. So let's look at 26 then, I guess. 26. How many f orbitals have n equals 6? So n equals 6. L can be 0, 1, 2, 3, 1, 2, 3, 4, 5, 6. So this is S, going to F. S, P, D, F. There we go. So how many f orbitals have n equals 6? Well, you have one f orbital at n equals 6. So m sub L, we take this one, and it would be -3, -2, -1, 0, 1, oops, 1, 2, 3. 1, 2, 3, 4, 5, 6, 7. You can have 7 f orbitals for n equals 6. Okay?
I don't get this at all. I don't know why. This doesn't stick.
Okay, so this one is whole numbers from 1 on up to whatever.
Right. Okay.
At each one of these levels, you look at the L. Right? So it's like it's a tree branching.
Okay.
So for each one of the ends, you have an L. So for 1, L can only be 0 because you can only have as many L's as you have number here.
Okay.
So if this were 2, though, you could have 0 and 1. But if n equals 3, you can have 0, 1, 2. If n equals 4, you can have 0, 1, 2, 3, because it's 1, 2, 3, 4. Okay.
And you give it 5.
Yeah.
But
And
not
just-
6.
So for 6,
Because it's already.
you can have 0, 1, 2, 3, 4, 5, because that's 6 levels.
So the electron can move. That's what we're.
That electrons can occupy
Okay.
around the atom. We're subdividing energy levels. Then, for m sub L, you subdivide each one of these. So if we're at L equals 0, then m sub L can be 0. That's it. Because m sub L is minus L up to plus L in whole number steps. So for 1, it can be -1, 0, plus 1. For 2, it can be -2, -1, 0, plus 1, plus 2. That's for each one of these levels, right? And each one of these came from each one of those. So it is a geometric progression.
So shouldn't there be more? Like, couldn't there be for ML like -4 and -5?
Oh yeah, right. This is for that one only. If we were to take this one, then it'd be -4, -3, on up to +3 at 4. For each one of these, then you have these optional levels.
Oh wait, this is where, okay, I'm getting it. I really have the.
Okay, yeah.
But where I'm confused is like, okay, what is the F orbital? Like, like you put S for 0, P for 1, D for 2, F for 3.
Right. These are substitutions for those values of the quantum number.
So what would 4 be?
G, and 5 would be H. But we never get that high. I mean, we've run out of elements. These are theoretical. You could go that high, you know, you can calculate the energy level, but there's no place for it because there's no atom for it. There's no element.
So F orbital is always an L. I mean, orbital.
Yes, right. The SPDs and S are always L's. Yes. So that's why when we write the configuration, the electron configuration for an atom, we put the principal quantum number, and then instead of writing 0 out there, which would be confusing, instead of writing 0, we write S. Okay. And then for the second level, for 2, you could have 0 and 1. So you could have 2S and 2P. For the L equals 1. Then when you get to the third level, you can have S, P, and D. So D is for the 2 L number. So this is N and L together. Okay. So if we wrote 4 out there, now we're getting to the point where we need to go back to that diagonal diagram because they don't fill in the order that we write them necessarily. They fill in the order of that diagonal, which tells us the actual energy arrangement. Let's see, up to what point? Right. So 1S, 2S, 2P, 3S, 3P, 5. Then we go to 4S. Then we go back to 3D. So in order of energy filling, it's this 3S, 3P, 4S, 3P. The other way that you can remember that is periodic charge. Because you're going 3S, 3P, then 4S, then 3D, then 4P, 5S, 4D, 5P, 6S, and then 4F. So you get those done, and then back up to 5D. And that will correspond to that diagonal diagram. It fits exactly the way we've got it laid out here on the periodic table.
This is going to be included on the exam though, right?
Oh yeah. If it's in this document here, everything in this back part will be on the exam. So if you learn how to use that, it'll be there. that was 26. Let's see if there are any other freaky ones in here that we need to look at. 26. Let's go ahead and do 27. 27 says, if n equals 2, how many orbitals are possible? So we want to know all the orbitals at the n level. So for n equals 2, L will equal 0, 1, or 2. No, I'm sorry. 0, 1. I'm sorry. 1, 2, 2, 1, 2. Okay? So then the M sub L will have two possibilities. This one can be 0, or it can be -1, 0, +1. So that's all the orbitals. The spin quantum number refers to individual electrons. So the orbitals themselves, the maximum orbitals you can have is 1, 2, 3, 4. Right, we got this one from that one, and these 3 from that one at that level. So we have 4 possible orbitals for n equals 2. Maximum total.
We don't count MS, because you said that's actual electron.
Right, right. That's only, for each one of these orbitals, you can stick 2 electrons in there, +1/2, -1/2. 2 in here, 2 in here, 2 in here.
So would 2 be considered an orbital?
Which one?
Just 2?
That?
Yeah.
That's an energy level. Principal quantum number is energy level.
Okay.
Yeah, you know, that's a beef I have with chemists and physicists, is terminology. You guys need to be consistent. Because some books will say it this way and some will say it another way. They might say that's an orbital and this is a suborbital. Or maybe this is an orbital and that's a suborbital. So
we're counting it 0, -1, 1, right? To get to 4.
yes,
Okay.
the total number, I'm assuming that when we want to know an orbital, that is the definition of a space that will hold 2 electrons.
Okay.
So that's each one of these would be 4. Total. I got this one from there and these 3 from there.
I get how we got them. I'm not going to sound like an idiot, but like I'm wondering how many, like which ones are we counting as 4? Because I'm seeing 7 total numbers. Like which ones are the 4?
Oh, right. We're drilling down through the crust.
Yes.
So this is the top layer, and then we drill down, and we can have this one, or we can have that one underneath here. And then with this one, we can only have that one, but this one we can have these 3. So once you get down to that level, you just forget that you ever came from there.
Yeah.
You're only looking at what's at this level. And at this level,
So
you can
we're
have,
looking at just ML.
yeah, you can have 4. Right.
Okay. I'm just wondering because I thought maybe if I had a different number, it might. I just wanted to make sure I knew how to do it. Okay, thank you.
If we were to do this, say, with 3, what would that tell us? See, this is not, I don't know, maybe it is. N equals 3. No, it's not. So let's say, if we were to say n equals 3, then L could be 0, 1, or 2. Then for 0, we could have 0. For 1, we could have -1, 0, +1. And for 2, we could have -2, -1, 0, 1, and 2. So for 3, we could have 1, 2, 3, 4, 5, 6, 7, 8, 9. 4.
Yeah.
5, 6, 7, 9 levels.
I wasn't for sure if you count them all the way going out or if you just count that last one. So now I understand. Thank you.
So that means if n equals 3, we should have 2, 5, 6, 8, 9, 10, 11, 12, 13, 18. Yeah, okay. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So for energy level 3, we're counting all the elements that are filling the third energy level. We've got 1, 2, 3, 4, 5, 6, 7, 8. Right? And then 9, because this is 3D. 10, 11, 12, 13, 14, 15, 16, 17, 18. So we have 9 levels here, but 2 electrons each means 18 possible elements. Okay. It's got to make sense, or it will crumple up in a ball and disappear. Now let's see if we can fill orbitals. Let's see. How many electrons? Quantum number. Oh, okay. 42. We get to start filling orbitals. Ooh, that's a tall order. That's very 56 electrons. Let's just do it. We'll do it the long way first. So barium at 52, did I say? No, 56. 56. So 56 is Z, or the number of protons, which means for the neutral atom, that's the number of electrons too. So we've got 1s, 2s, 2p, 3s, 3p, 4s, 3d, 3d, 4p, 5s, 4d, let's see, 5s, 4d, 5p, 6s, right? That'll take us to barium. So you got to remember, what's the maximum number of electrons you can have in each one of these? S's are always 2, because there's only one. Remember, 0, that's it. You can only have 1, so that means 2 electrons maximum. That's why S only has 2. 2. P is 1. L equals 1, which means M sub L is what? M sub L is minus 1, 0, plus 1. So that's 2, 4, 6. Right? 6 electrons in the P. 2, 6, 2. How about D? Well, this is S, this is P. D is 2. So that one is minus 2, minus 1, 0, 1, and 2. 2, 4, 6, 8, 10. 10 electrons in the D. Okay. I don't want to lose you. Right? So if D equals 2, that means M sub L is minus 2, minus 1, 0, 1, and 2. 2 electrons each means 10 electrons. So the D's can have 10 electrons. And we have 6, we have 2, and D again will be 10. So let's add it up to be sure we don't overshoot. 2, 4, that's 10, 18, 20, 30, 36, 38, 48, 54, and 2 is 56. Okay, so that's the complete electronic structure for barium. Now for the shorthand, which I think is the answer for this one. Yeah, this one uses shorthand. So for the shorthand, use your periodic table. Find your element, and then work backwards to the nearest noble gas. So work backwards, 1, 2, like over here, xenon, 54. So xenon 54 is our core, and then what's left over? Well, up to here is 54, right?
Yes.
Up to there is 54, so that means we only have 6s2 left. And the other way is, watch your periodic table, that's 54. What are we filling here? 6s12. And you can write the structure just that fast. Xenon 54, 6s. This is considered the core. Right? These are core electrons. These are valence electrons. So that's why barium, when it ionizes, gives up those 2 electrons so that it can look like xenon. Because everybody wants to be a noble gas. So barium, when it ionizes, is going to be 2+. So that rule that we learned, the second group is always 2+. They're 2+ because of that. Okay? What did I do? Let's see, we want to do another one. Ooh, let's do carbon. Then maybe it'll take organic chemistry. Let's see, 43. So the electronic structure for carbon, and we're going to do this one complete. So carbon has how many protons? 6. Okay, so that means 6 electrons. And we do 1s2, 2s2, that's 4, we need 2 more. 2p2. That's the electronic structure for carbon. But you're going to find out later that this orbital is different than that orbital. So when you form bonds with various elements, it doesn't form a separate bond with that one and a separate bond with that one. Carbon usually forms 4 equivalent bonds. So we hybridize these 4, these 2 and these 2 together and make a special hybrid orbital that is symmetrical. Okay, that's just a tease. But that's the structure for carbon. Okay. We've got another 10 minutes without any exertion. We talk about, let's see. Was there any discussion, I don't remember doing it in class last time, on paramagnetic or diamagnetic? Did we talk about that? Okay, so I won't open that can of worms. Because the electronic structure, actually, the electronic structure at this point doesn't fully explain paramagnetic and diamagnetic, so I won't even define it. In order to get to that, we need molecular orbitals. Are we going to do that? We do that later. Yeah, my chapter 8. No, chapter 9. Eight and 9. Yeah. We talk about molecular orbitals in chapter 9, so we'll hold that discussion of diamagnetic and ferromagnetic. Because only with molecular orbitals can you fully explain the difference between the two. So just store that one away. Okay. Anything else giving you trouble?
We're doing 52, 54.
53,
Yeah.
54, okay. Oh, okay. 53, so we're working from that diagram to decide which one is ground state nitrogen. So nitrogen has 7. Ground state nitrogen is, we talked about that a little earlier. What does the ground state mean? The ground state means that the electrons, all the electrons in the atom are at their lowest possible energy level, which means you fill them up, nucleus, so you have 1, 2, so we could have 2 at that level for nitrogen and then 5 at this level. And these orbitals are empty. If we promote one of these electrons into a higher orbital, it's not ground state anymore. It's excited. So ground state is unexcited. The electrons are as low as they can get, close to the nucleus as possible. That's ground state. So basically that's just write the electronic configuration as you would normally. That's your ground state. Hey,
Hi.
about time.
I know. My lab, I just sent to you online. That's where I've been trying to print it off for the past like 2 hours. And my computer decided it wasn't going to work. So I figured out to send you like a PDF.
Well, yeah, I mean, you could have come to class and just sent it to me later.
Yeah.
It's all recorded. Okay, so ground state then would be, if we write this like we've been doing, 1s2, 2s2, 2p3, okay, 7 electrons. But if we want to identify it with this figure, then you've got to say, what are the, and I don't like boxes, I just like lines. You got 3 p orbitals, remember? P equals 1, so it can be -1, 0, or +1. Right, so you can have 3 in the p's. So these 2 go in like that, 2 electrons here, and then 3 electrons here goes like that, like that, like that. You have to put, they have to be in separate suborbitals before you can go back and start pairing them up. Right? So we wouldn't put one of these over here and leave that one blank. That's Hund's rule. You have to fill them up, up. And then if we went to oxygen's next, oxygen would have another electron, then you could put it in there, paired up. So that's, yeah, which one is it?
It looks like they don't even do 1s. I guess.
Oh, no, they left out this part. Right, they were only using that much.
So the ground state would be A.
A, yes, that's correct. 54. So 54, we've done that. What does that mean? That means we've added an electron. Right? So underneath here, like that, we'd still have these. 1, 2, 3, and then the added electron would go there. E. Mm-hmm.
Wait. Oh, yes.
Yep. That was the only 2, wasn't it?
I think so.
Okay. Any others? Okay. We can look at the lab now. All right, put this away. Realtor, factory. I think I had another handout too. I don't know if you need, the lady that teaches MLT, do you have a copy of this one? Molecular weight of an acid? Yeah, I see it. Okay. As long as everybody's got a copy. I brought some extras. This is a little handout on pipetting techniques. You don't have to memorize this or anything. It's just, it might be useful at some point in the future. I'm going to describe it to you anyway. But here it's in print. But I thought this was a pretty neat little concise description of how to do it. So let's talk about the gist of this. Let's look at materials first. Okay. We're going to have citric acid. Everybody knows citric acid. Just bite into a lemon. You'll find out about citric acid in a hurry. Phenolphthalein. So what's phenolphthalein? It's a dye, and it responds to changes in pH. Right? So phenolphthalein in solution, and in order to use it as an indicator, you just put a couple of drops in your reaction vessel, and as long as the pH is acidic, it's clear. When the pH goes basic, it turns pink. Right? So we're going to have an acid in our reaction vessel, and then the burette. Everybody seen a burette before? Better describe a burette. Burette's a long tube with a valve here, and it's got graduations here in milliliters. And then it has a delivery tip. So you open and close that valve, and it lets whatever's in your burette into your reaction vessel, okay, for the reaction to go. The reason we use a burette is we want to know exactly what volume of this was delivered into the reaction vessel. So it starts at 0 up here and goes to 50 down here, milliliters. That's because we're showing how much did we deliver. If we start at 0, then we only have to read what's the value here. That's how much we delivered. Of course, if you don't start at 0, you just have to say this value minus that value is the actual amount. Okay, and it's usually marked off in has marks in tenths of a mil, so it's fairly accurate. So this indicator tells us when the reaction has gone to completion. Right, we want to know when, and the way we're going to do it is we're going to have acid down here, and we're going to have base up here. So when we put phenolphthalein in, it's going to be clear. And when we've reached the end point of our reaction, it's going to turn pink. That's when you stop and take your measurement. Okay? So we're going to do actually 2 titrations. And a titration means an equivalence. Well, it depends on the reaction, but in our case, the titration refers to an equivalence of acid to base. So the titration itself is the process of adding base to our acid. Okay, and you're looking for a point where the moles of base that you add is equal to the moles of acid that are in the container. Okay, so when they're equal, color change, and you know to stop, and you can say, okay, we put in the same amount of base, moles of base, as we have acid. So, 2 titrations that we're going to do. First one is between acetic acid and sodium hydroxide. Okay. So we're going to have acetic acid down here, and we're going to add sodium hydroxide until we reach that end point. Then our calculations will tell us the number of moles. We know the number of moles here exactly, because we're going to add exactly 10 milliliters of this acetic acid, and it has a known concentration of 0.873 molar. It's very stable over long periods of time. So I bought it, and it is that concentration. Okay. So that's our first titration. The second titration, instead of acetic acid down here, we're going to put citric acid. And do another titration with sodium hydroxide. Only this time, instead of having a question about its molarity, this is going to tell us what the molarity of sodium hydroxide is with our calculation. Now that we know what is exactly the molarity, then we can use that to tell us how many moles of this we have in our beaker. Okay, so we're going to do those 2 titrations. All right, calculations. How do we know this and this equivalence? The calculation is acetic acid plus sodium hydroxide yields sodium acetate plus water. Okay, that's a balanced equation. And the nice thing is, it's 1 to 1. So 1 mole of that reacts with 1 mole of this. So in that case, we can say, if we know how many moles of this we have in the beaker, we can say how many moles of that were delivered, right? Because we know the stoichiometry. So let's say we have 0.873 molar. And remember, the definition of molarity is moles per unit volume. So if we want to know how many moles, we say molarity times volume. Right? So molarity times volume, and how much volume do we have? 10 milliliters. Okay, so that's how many moles of acetic acid we have in the beaker. And that's equal to the molarity of the base times how many mils we deliver. And since the mils here are the same, we can use mils. We don't have to use liters. You know, molarity is moles per liter, but if we have milliliters both on the same side, we can use them. So this is what we're going to get from our titration. That volume right there is going to fit right here. So then we have that one, and that one. We solve for this one. And once we have this value, then we can go to the next step, citric acid.
Where do we get the 0.873?
I set that alarm. So I would know we need to get onto this, just as a reminder. Okay, your question?
Where do we get the 0.873 molarity?
I gave it to you.
Oh.
It should be in here too, because this method is based upon the chemistry. There it is. Say on page, well, no, this is the instructor's version. Let me look at yours. Let's see if it's given in yours too.
And that's just the molarity of the acetic acid?
Yes. Okay, so it's not given. I have to tell you, the molarity of the acetic acid is 0.873. Yes, I have to tell you that. Okay. So let's see. Let me look at your version. Laboratory questions. Okay, so this is one that we can do in class. All right. I'm gonna have to erase this. So this is the first discussion question. It's not in your material. I have to give it to you. So the question is, we want to calculate the volume of 0.75 molar sodium hydroxide required to reach the endpoint with 0.873 molar acetic acid when you're using 25 milliliters of acetic acid in our reaction vessel. Okay? So we want to know what's the volume of base required to reach the endpoint with that. So this is really simple. Since we know the stoichiometry is 1-to-1, we can just say moles is equal to moles. So this is moles of base. This is moles of acetic acid. And they're going to be equal. Moles of base. Because that's where the endpoint is. Okay? So moles of base is going to be 0.75 molar times volume, which we don't know. That's the question. Right? And then this one is going to be 0.873 molar times 25 milliliters. Okay? So we just solve for V. That times that divided by this, which should be 29.1 milliliters of sodium hydroxide. Okay.
what is that?
This is the volume of sodium hydroxide required to reach an endpoint reaction with that much acetic acid. Right, we said moles of sodium hydroxide is equal to moles of acid because it's 1-to-1.
It's just how much is needed to react with that?
Uh-huh. That means we're going to reach an endpoint. In other words, the phenolphthalein is going to change color. So let's see if that makes sense. Right? If the acid is more concentrated than the base, it should take more base to react with the acid. So it should take more than 25 milliliters of this to make the same moles. Right? And it does, 29.1. Okay, so let's do another one. Slight modification here. Calculate the volume of 0.75 molar sodium hydroxide solution. 0.75 molar sodium hydroxide. And then volume, we don't know, is required to react with 1.20 grams of citric acid. This one is a little more complicated, but if we're going to approach it methodically. First of all, we need to know how many moles of citric acid it is, because grams doesn't mean anything, not in a chemical reaction. So we need to convert this many grams of citric acid to moles of citric acid. So we need to know the molar mass of citric acid, which is 192.13. Okay, so that gives us 0.00625 moles of citric acid. Then, and you wouldn't know this unless I told you, how many protons does citric acid have available to react with that base? It's not like acetic acid that only has 1 proton. Citric acid has 3 protons. So, if this is the concentration of citric acid, what's the concentration of its protons? 0.01875 moles of protons available from that. See what I mean?
Divide by 3?
Multiply by.
Oh.
Okay, see. 3 times 6 is 18.
Why did you do that again?
Oh, because the base only has 1 hydroxyl to neutralize a proton. But the acid has 3 protons for every mole of citric acid. So the reaction is going to be, let's see. Let's write it this way. Rather than write the whole formula, let's just say citric acid has 3 protons. Okay? Like that. It's got 3 protons on every molecule.
Hydrogen.
Yes.
In hydrogen.
Yes, that are available. And sodium hydroxide then reacts with that to produce. So when we get rid of these 3 pluses, we have a 3 minus there, right? 3 minus, that means we need 3 sodiums, because each sodium is only 1 plus. So in order to balance it, we need 3. So we need 3 of these, and that gives us 3 waters. Because we have 3 of these plus 3 of those makes 3 waters. Okay? Okay. So this is the stoichiometry for citric acid. Since we have this many moles of protons, let's see, go back here. Oh, now we're going to have that many moles of protons neutralized by how many moles of sodium hydroxide, because it's only 1 each. So we got 0.750 molar times volume is equal to 0.01875 moles. Because this is going to be moles of hydroxyls that's going to neutralize that many moles of hydrogens. Okay, so they have to be equal. So now we can solve for V, which would be this divided by that, which is, where am I? Here we go. 0.025 liters, which is 25 milliliters. So 25 milliliters of that concentration sodium hydroxide is required to react with 1.2 grams of citric acid. So that's the fundamental difference between the first titration and the second titration. The first titration, where you're standardizing, that's what we're doing. We're standardizing our base with a known concentration of acetic acid. We measure a volume of acetic acid here and titrate it to endpoint. But with the citric acid, it's a solid. So we're going to dissolve it in a certain amount of water, which your method spec dictates. And then once it's in solution, we add our phenolphthalein as an indicator. Then we titrate it. And it doesn't matter how much water we use, right? Because we're only titrating moles against moles. So the volume is irrelevant. You just need enough volume to dissolve the citric acid. Then you can tell you're gonna weigh out the amount of citric acid into the reaction vessel or into a weigh boat and then transfer it. So you know the mass of your citric acid that goes in there. It doesn't have to be exactly 1.2, whatever it turns out to be. Then when you titrate the known base, you're going to have a volume that you deliver, and that volume times this molarity, or whatever the molarity is, the standardized molarity, will give you the number of moles of hydroxyl. Okay? So that's the number of moles of hydroxyl, which is equal to the number of moles of hydrogen. So then if you know the number of moles of hydrogen, how many moles of citric acid do you have? 1/3 of that. Right? We're working backwards this time. So you got 1/3 that number of moles of citric acid. Now you've got the mass of the citric acid you put in there. You got the moles of the citric acid you put in there. Grams per mole, molar mass. I'll be saying England, Bob's your uncle. You ever heard that one?
I've never heard that one.
So that's the whole thing in a nutshell. Those two questions. I know it seems like a lot. Once you get in there, we'll take it methodically. How much time do we have?
3 o'clock, and we're good till 5 something, right?
Yeah.
5 o'clock.
Okay. That's good. 2 hours should be enough. Of course, you probably want to take a little break first.
And I need to
get some equipment out for you. So I'm gonna take this with me. And let's stop this so it can start converting itself.